Environmental and ice control systems have been developed to allow pilots to comfortably fly at relatively high altitudes and in a variety of weather conditions. Ventilation, air conditioning, and heating systems compensate for hot and cold temperatures, while oxygen and pressurization systems overcome our physiological limitations. In addition, to take advantage of the increased aircraft capabilities, ice control systems were developed to allow pilots to fly into known icing conditions. The following discussion covers some common environmental and ice control systems. But before you use any of the systems in your aircraft, you should consult your pilot's operating handbook. Let's begin with air conditioning systems. The most common type of air conditioner found on general aviation aircraft is a vapor cycle system. These systems are very similar in operation to the systems found in an automobile or refrigerator. To activate the system, controls are provided in the cockpit. Normally, these controls include an on-off switch, a thermostat control, and a fan control. When the system is turned on, a pump compresses Freon vapor and sends it to a condenser, which is exposed to the free airstream. Here, the Freon cools and turns into a liquid. Then the Freon goes to a receiver dryer, which acts as a reservoir to ensure there is enough coolant available to meet system demand. In the receiver dryer, the Freon goes through a filter dryer. The filter removes contaminants, while the dryer contains a material that attracts and removes moisture, which could freeze in the refrigeration system and plug the line. The Freon then goes to an expansion valve where the pressure is reduced. This further cools the liquid. From there, the Freon goes to the evaporator, or heat exchanger. Here, the liquid Freon changes to a vapor. Cabin air is then passed through the evaporator. Since the cabin air temperature is warmer than the temperature of the vaporized Freon, the Freon absorbs heat from the cabin and makes it more comfortable to you and your passengers. Finally, the vapor is returned to the compressor and the cycle starts over. For winter flights or flights in colder temperatures, a cabin heater is often more essential than an air conditioner. There are two basic types of heaters: the heat exchanger and the combustion type. The first one we'll discuss is the heat exchanger, which is commonly found on single-engine airplanes. These systems pass cool ambient air through a shroud surrounding a hot component in the engine compartment, usually the exhaust system. This heats the air, which is then vented to the cabin. One danger associated with this type of system is the possibility of carbon monoxide leaking into the heating system through a defect in the exhaust system. Carbon monoxide can quickly and severely reduce your flying ability and can even cause death. If you suspect a leak or smell exhaust fumes in the cockpit, turn off the heater, open the fresh air vents or windows, and use supplemental oxygen if it's available. The other heating system is the combustion type, which is like the gas furnace in most homes. This type of heater is commonly found on multi-engine airplanes because the location of the engines make heat exchangers inefficient and impractical. This system uses a blower to force hot air from the combustion heater to the cabin. Although combustion heaters operate independent of the engines, they rely on the same fuel supply. Therefore, you should plan on increased fuel burn and decreased range when using this type of heater. If the heater overheats, an overtemp switch shuts the heater off to prevent a possible fire. In most aircraft, this overtemp switch cannot be reset from the cabin. Therefore, you'll have to continue the flight without heat, or land and reset the system. However, before flying again, make sure you've determined and corrected the malfunction. Another environmental control system commonly found on high-performance aircraft is an oxygen system. Federal aviation regulations require the use of supplemental oxygen above certain altitudes in order to compensate for the body's inability to get enough oxygen through normal respiration. There are three types of oxygen systems: continuous flow, diluter demand, and pressure demand. The first one we'll look at is the continuous flow system. This system is commonly found on general aviation aircraft and can be portable or permanently installed. Whether permanent or portable, the continuous flow system has four basic components: a high-pressure supply cylinder, a pressure regulator, a distribution system, and a continuous flow mask assembly. The oxygen supply is stored in one or more high-pressure cylinders. These cylinders must comply with strict quality standards and labeling practices. These labels identify the cylinder as containing aviators breathing oxygen, the date of the last hydrostatic test, and the highest pressure the tank can be charged to. Normally, this is 1,800 pounds. A gauge displays the pressure in the cylinder, while the on-off valve is used to start oxygen flow. On portable units, the gauge and valve are on the tank, while permanent installations often have these controls in the cabin. A pressure regulator reduces cylinder pressure to a usable level. This regulator may be manually operated or automatic. A manual regulator works the same as a water faucet. Opening the valve increases flow. The disadvantage of a manual regulator is that you must readjust it as you're changing altitude. With an automatic regulator, all you have to do is activate the system with the on-off valve. The system then compares the atmospheric pressure and cylinder pressure and adjusts the flow accordingly. In aircraft with permanent installations, oxygen outlets are located in various places throughout the cabin. Each outlet has a spring-loaded check valve to prevent oxygen leaks and allow oxygen to flow only when a mask is plugged into the outlet. The mask assembly for a continuous flow system consists of the plug-in connector with the flow restrictor, a supply hose with a flow indicator, a rebreather bag, and the mask itself. The plug-in connector has different size openings depending upon who will be using the mask. A larger opening connector is used by pilots and crew since they require more oxygen than the passengers. These connectors are usually color-coded with the passenger's supply hose marked with a gold or orange band. The pilot supply hose is marked in red. The flow indicator shows that oxygen is flowing to the mask. This device is simply a spring-loaded check valve. When the oxygen is flowing, the pressure overcomes the spring and deflects the colored valve toward the mask. The rebreather bag helps conserve the oxygen supply by mixing the oxygen with outside air. Oxygen flows continuously into the bag, causing it to expand. As you inhale, the bag collapses and outside air is drawn in through small holes in the mask. The bag is partially refilled by unused air exhaled by the user and partially by oxygen from the storage cylinder. Unused air is forced out the holes in the mask. As altitude increases, the greater flow of oxygen causes the bag and mask to be pressurized more. This results in less outside air entering the mask. In addition, the higher altitude causes the bag to expand due to the lower surrounding pressure. The continuous flow system is adequate up to 25,000 feet. Above 17,000 feet, however, you must be careful to maintain a tight seal between the mask and your face. Above 25,000 feet, you and your passengers should use some form of demand oxygen system. The diluter demand is one of these systems and is the next one we'll discuss. A diluter demand system shares the same components as a continuous flow system except there is no rebreather bag. Instead, an additional regulator is incorporated in the mask or hose assembly. As the name implies, the diluter demand system supplies oxygen only when you inhale, and virtually all the exhaled air is forced out of the mask. As altitude increases, the regulator increases oxygen flow. Normally, you'll receive 100% oxygen by 30,000 feet, but you can select 100% oxygen at any time. The third type of oxygen system is a pressure demand system. These are more commonly installed in turboprop and jet aircraft because of their high cruise altitudes. These systems are primarily used in case the cabin pressurization system fails. At high altitudes, there is not enough atmospheric pressure to allow you to breathe normally, so oxygen is forced into your lungs. The use of pressure demand oxygen requires additional training since special techniques are required for its use. Regardless of the type of oxygen system installed in your aircraft, it's very important to have a sufficient supply of oxygen available for the planned flight. To make sure you have enough oxygen, you should use an oxygen duration graph or chart. To use this particular type of graph, you have to know how much oxygen is available and how many people will be using the system. The oxygen available is indicated in pounds per square inch of pressure on a gauge. In this example, you have 1,800 pounds in the cylinder. To find out how much oxygen is available for the pilot and 2 passengers, locate 1,800 psi on the chart, then move to the line representing the consumption rate for the pilot and 2 passengers. Next, locate the duration of oxygen available. In this case, it is slightly more than 2 hours. The pre-flight inspection should also include a check of the system itself. This can be done by turning the oxygen system on and checking each outlet for flow. Finally, brief your passengers on the use of oxygen and stress the importance of not smoking, since smoking poses a serious fire hazard. If the oxygen system fails during a flight, or if oxygen is not used for high-altitude flights, you may suffer from hypoxia. Hypoxia is caused by a lack of oxygen. Symptoms for hypoxia vary from one person to the next, but one of the first things to be affected is your judgment. Here is a list of the common symptoms. Since hypoxia impairs judgment and may not be easily recognized, it is very important to take corrective action before hypoxia develops. The FAA recommends that oxygen be used above 10,000 feet during the day and as low as 5,000 feet at night. A condition with similar symptoms to hypoxia, but from an entirely different cause, is hyperventilation. Hyperventilation is a deficiency of carbon dioxide, which causes a chemical imbalance in the bloodstream. Hyperventilation results from deep, rapid breathing, which is normally an involuntary reaction to stress, tension, anxiety, or fear. Since the symptoms of hyperventilation are similar to hypoxia, it is often best to treat the victim for both. With hypoxia, 3 or 4 deep breaths of pure oxygen should relieve the symptoms. If this doesn't work, have the individual breathe into a sac and make a deliberate effort to relax and slow the breathing rate. Talking aloud may also help. Since oxygen use may make some passengers nervous, pressurized airplanes are often more desirable. Other advantages include freedom to move around the cabin and talk more easily, as well as an increased comfort level because of small changes in atmospheric pressure. An aircraft pressurization system receives compressed air from a turbocharger or the compressor section of a turbojet engine. The advantage of obtaining air from these sources is the fact that the compressor system is already there. The disadvantage is that this air is very hot. Therefore, the compressed air is passed through a heat exchanger to cool it down. Since the cabin must contain the compressed air, it is designed and built at the factory to maintain a predetermined pressure differential based on performance goals. In this example, the airplane's cruise performance is best at 24,000 feet, where the pressure is 5.8 psi. However, the desired cabin altitude is 8,000 feet, where the pressure is 10.5 psi. This means the cabin must maintain a pressure differential of 4.7 psi. The pressure differential is maintained by an outflow valve. This outflow valve automatically opens and closes to maintain a selected cabin pressure. Failure of the outflow valve may cause excessive pressure to build, so a safety release valve is installed in the cabin. If cabin pressure approaches the design limits of the airplane, this valve opens to relieve the pressure. This valve can also be connected to the landing gear safety switch so that anytime the gear is down and the switch is open, the cabin depressurizes. It may also be manually opened in case a turbocharger fails and contaminated air enters the cabin. There are two types of pressurization systems: a basic system and a controllable system. All you have to do with a basic system is turn it on. When the airplane reaches a preset altitude, commonly 8,000 feet, it will begin to pressurize. As the airplane continues to climb, the cabin altitude will remain at 8,000 feet until a second preset altitude is reached. Past this point, which is commonly 20,000 feet, the cabin altitude increases as the airplane climbs. A controllable system is more complex, but it allows flexibility and control that the basic system lacks. With a controllable system, the pilot can choose where pressurization begins. For instance, you can begin pressurizing the cabin at pattern altitude, and the cabin remains at that altitude until it reaches the maximum allowable pressure differential. Then, the outflow valve maintains this pressure differential as the aircraft climbs. The outflow valve in a controllable pressurization system can also be controlled to adjust the rate at which the cabin is pressurized or depressurized. This means the airplane can descend at 2,000 feet per minute to comply with ATC instructions. But to keep the passengers comfortable, the cabin pressure can be adjusted to descend at 500 feet per minute. To increase the utility of an aircraft, it may be necessary to operate in conditions where icing is possible. While your primary goal is to avoid icing conditions, anti-ice and de-ice systems allow you to control or prevent icing to a certain degree. To legally fly in known icing conditions, an aircraft has to be certified by the FAA for that type of operation. This certification includes installation of anti-icing and de-icing systems designed to keep the airframe, propellers, and windscreen free of ice. Let's take a closer look at some of these systems. Anti-ice systems prevent ice formation, whereas de-ice systems are used to free the aircraft of ice that has already accumulated. Probably the most common anti-icing device is the pitot heater. A heater coil of high-resistance metal is built into the pitot tube housing. When the switch in the cockpit is activated, the coil's high resistance causes it to heat up and prevent the formation of ice. Many piston-powered aircraft have pneumatic airframe de-icing systems on the leading edges of wings and tail surfaces. Normally, this system consists of inflatable boots, engine-driven pressure and vacuum pumps, a timer, and pneumatic regulators. The engine-driven pressure pump inflates the boots while the vacuum pump deflates the boots and supplies enough suction to keep the boots flat against the leading edge of the wing. The timer controls the inflation-deflation cycle. The regulator ensures the boots don't overinflate. It also may alternate the inflation and deflation of various sections of each boot to minimize the disruption of the airflow caused by the inflation of the boots. While you should follow the manufacturer's recommendations as to when to operate the system, the general procedure is to allow 1/4 to 1/2 inch of ice to accumulate before activating a pneumatic system. If the ice is too thin to break away cleanly, it may refreeze, leaving a space between the ice and the wing. Further attempts to de-ice the wing may be ineffective because the boots inflate within the cavity and don't break the ice. The second type of airframe ice control is the anti-icing system found on turboprop and jet aircraft. This system uses heated engine air routed to the leading edges of the airfoils to keep them above freezing. Heat is also used to control ice on propellers and windscreens, but heated engine air is impractical, so electrical energy is used instead. Oil and wear-resistant pads embedded with electrical heating elements are bonded to propellers. Electricity is supplied to these pads through wire brushes in the propeller hub. Since centrifugal force is sufficient to throw ice off the outboard section of the propeller, the pads usually heat only the inboard section. Some propellers are protected against the formation of ice by coating the blade surface with alcohol, usually isopropyl alcohol. With this system, alcohol is sent to a slinger ring. Injector tubes on each blade pick up the alcohol from the slinger ring and direct it to the propeller blade. Windshields may be protected with alcohol, but normally they are electrically heated. Tiny electric heating elements are laid in the windscreen or windshield panel to heat it up and melt any ice. Before flight, anti-icing chemicals may be applied to the airframe, propellers, and windshield to lessen the chance of ice adhering to these parts. Used together with anti-icing and de-icing systems, these chemicals can be very effective. Of course, flight in icing conditions may be hazardous regardless of how your aircraft is equipped. Before you enter areas of known icing, you should be sure that all of your systems are operating correctly and that you're familiar with the specific equipment installed on your aircraft. It's also a good idea to limit your exposure to icing conditions. Some of the systems described may handle ice better than others. The aircraft systems we have discussed in this section are designed to increase comfort and to allow you to adapt to an environment of reduced atmospheric pressure and oxygen levels, as well as the danger of structural icing. Thorough knowledge of the systems installed in your aircraft and good operational practices will lead to many enjoyable hours of flying.